We're now going to have a look at one of the most famous rules of calculus, and it's famous perhaps because of its name, L'Hospital rule. Now, is this some rule that was created in a hospital? No, actually, it's a rule that was made popular by this fellow that you see here, the Marquis de l'Hospital. You'll see sometimes you're going to see his name also spelled this way, and he was a French fellow, and you know that the O with the hat on top is one of the vowels which are used in the French language. And so there is a controversy about which way to spell his last name, but apparently I've read somewhere that he preferred spelling that I gave you originally, so with the OS instead of the O with a hat on top. So I'm going to stick to that one, although you're free to use either one of them, and you're going to see both of them. Now, what is this rule? This is a rule which allows us to compute and to resolve many indeterminate forms in a fairly easy way. Some situations where the algebraic method of computing limits doesn't work, this can come in quite handy. Okay? But it is also a rule that we need to apply with care. Okay, so let's see what the rule actually says. Oh, by the way, let me go back to Monsieur de l'Hôpital. You might think that this rule is called L'Hospital's rule because this fellow invented it or developed it or discovered it, whatever way you want to say it. Well, in fact, that's not true. L'Hospital was a good mathematician, but he was not a great genius. He did not invent this rule. His claim to fame and the reason why his name got attached to the rule is because he published the first commonly used calculus book, and in his calculus book he put this result, which up to that point had been somewhat underestimated, and so because of his putting it in the book, then it became quite common and famous. So if you want, think of him as some kind of PR man, someone who took an interesting technique and made it famous, and that's why his name got attached to it. So what does the rule say? First of all, let's assume that the following facts are true for some value c, which may be finite or infinite. So what I'm going to say will apply to both c finite or infinite. Okay. First of all, let's say we're dealing with two functions f and g which are differentiable near c. Okay. We're also going to assume that that g prime of c is not going to be equal to 0 in an interval around c, except possibly at c. Okay? So in other words, this function g of c is not always 0. Okay? Let's also assume that the limit as x approaches c of the ratio of f and g with g in the denominator, and now you can have a glimpse of why we need that second condition, is either 0 over 0 or infinity over infinity, plus or minus, doesn't matter. So also let us assume, and this is an important thing, let me back up here again for a minute. This may call it L'Hopital's rule or the backing up class. These three conditions are the ones which are usually associated in the minds of people who use this rule to the rule itself, and then sometimes people jump to the conclusion from here. But actually we need another condition, and this is a condition that sometimes is thought of as the conclusion, but it's not. It's a condition. Okay, so the fourth condition is that the limit as x approaches c of the ratio of the derivatives of those two functions is either some number that we can establish or is infinity, plus or minus, doesn't matter. So in other words, let's assume that the ratio of the two derivatives in the limit can be resolved. It's not an indeterminate form. We know that it is a number or is plus or minus infinity. Well, if all those four conditions are true, then we can say then it is also true that the original limit, the limit of the ratio of the two functions, is equal to the limit of the ratio of the derivatives. As I said, you want to be careful because sometimes people jump from the first three to computing the limit of the derivatives and claiming that their limit is equal to the original limit. But in order for that to be true, first of all, we have to check that the limit of the derivatives, this thing over here, the number 4, that is actually true. Because if that is not true, then we can come up with all kinds of silly conclusions. Okay? So the way to interpret and use this rule in an operative context is to say, all right, let's say that we're looking for that limit. We check all four conditions, and if they are satisfied, then we can move to this limit and say, well, that is the same thing. Okay? So how are we actually going to apply this rule in practical situations? Because notice, let me go back again. We said this was going to be the backup lecture, so might as well. Notice that this rule applies only to situations to indeterminate forms of the type 0 over 0 or infinity over infinity. Does it apply also to other indeterminate forms? Well, here is how it works. In order for us to use L'Hospital's rule, we're going to do it as follows. If we have a 0 over 0 or infinity over infinity form, then we can apply the rule as stated. The way I presented, you can apply it straightforward. If you have a form of the type 0 times infinity, what we need to do is change one of those two factors and move it to the denominator so as to change that product form into a quotient form, which will then become either 0 over 0 or infinity over infinity, and then we can use L'Hopital's rule there. If we have an infinity minus infinity form, then what we can do is we can try to change it to a single fraction. Usually infinity minus infinity comes from a difference or sum of two fractions, and so by doing a common denominator we can try and change it to a single fraction, to which we can then apply L'Hopital's rule as it stands. And finally, if we have one of the power forms, 0 to the power 0, infinity to the power 0, or 1 to the power infinity, we can use logarithms. What we can do is we can say, all right, I'm looking at a form that looks like that. Limit as x approaches c of f of x to the power g of x. Well, I can always write f of x as e to the ln of f of x. Remember that in order for that form that function f of x to the power g of x to even make sense, f of x has to be positive, so we can write it as e of ln of f of x. And at this point I can combine the two exponents and I can write that as e to the power g of x times ln of f of x. Well, now what we have is we have a limit where x is only in the exponent. So the exponent is the only place where we need to work in the limit. And now we have something that can that looks generically, the way we're seeing right now, as a product, but in fact in general it could look like either as a product of the type 0 to times infinity, or as a quotient of the type 0 over 0 or infinity over infinity. So we're going to apply L'Hopital's rule to the exponent, and then whatever answer we get, we put it as the exponent of e and find out what the original limit was. And as usual, time for us to practice, and so see you in class.